Go team. Okay, so this is part 2 of particle in a box. What we're going to do now is we've got psi of x is equal to a sine n pi a over x, or n pi x over a, where k is n pi over a, and we found that from the boundary conditions. What we're going to do now is figure out what this a is. And if you recall from one of the previous videos and in class discussion, normalization is key. So we need to have a normalized wave function to make sure that we have 100% probability of finding the electron within the potential barrier. And so here's my box. From 0 to A, that means I need to have 100% probability that the electron would be found inside that potential or within that potential, or within the box or within the boundaries. So that means that if I were to take from minus infinity to infinity of psi star psi dx, I would get 1. A is my normalization constant. And so what we want to do is now solve for what A is. Now, from minus infinity to 0, psi star psi dx plus from 0 to a psi star psi dx plus from a to infinity psi star psi dx. I'm writing this all out because there is 0 probability of the electron existing from minus infinity to 0, 0 probability of the electron existing from a to infinity. Therefore, that means that this has to equal 1. All right. And so you might see in your homeworks that you have sometimes you have 0 to infinity or minus infinity to infinity, and sometimes you have integration limits of 0 to a. That's all based on the system that you're in. And so this is where it's important to recognize and draw a picture of what's your system. Okay, so we're going to focus in on this bit, and we're going to solve for what a is. Let's do it. Okay, so I've got a. So this is not a complex function, therefore psi star psi is the same as psi squared. So the integral of psi squared of this is a squared sine squared n pi x over a dx. And I'm going to say that equals 1. Go team. Solve for a from 0 to a. All right, so what we're going to do is we are going to look this up in an integral table. And when you do that, you find that the integral of sine squared x dx is equal to minus 1/4 sine 2x plus 1/2 x. If you find yourself solving an integral via integration by parts or another method, good for you, stop it. Unless you really want to practice it, don't waste your time. Look this up in an integral table. It's important. In the resource section in Atkins, you can find this. And so what we're going to do is we're going to make our system fit this result. So I like to do a U substitution just because U is a fun letter. So if U equals n pi x over a du is equal to, so the derivative of this with respect to x is n pi over a dx. Okay, so what I'm going to do then is then make sure that I have an integral substitution or U substitution that also takes into account my integral limits. Okay, so if I do that, then when x equals 0, this is this one, when x equals 0, U equals 0. That's easy. When x equals a, what is U? If x equals a, n pi a over a's cancel, U equals n pi. Okay, so using an integral table is great. It saves you so much time, but you need to make sure that you also change your integration limits. Cool. Okay, now let's rewrite this in terms of U. So I've got integral from 0 to n pi. I shouldn't go rogue. Every time I go rogue, I make a mistake. Integral 0 to n pi sine squared u du. But dx, so basically we're substituting in. So here, n pi x over a, that's this, so that's u. Dx is du times a over n pi, so a over n pi. Did that make sense? Let's try that again. So if I solve for dx, dx equals a comes up, and pi goes down. So I'm going to substitute dx in here, which means that this becomes sine squared u times a over n pi du. And a over n pi does not depend on u, so it comes out of the integrand, and I need to remember my a squared, and all of that equals 1. Go team? Okay, so now I've got, now I can just plug this in, and I've got a squared a over n pi quantity, and I'm going to impose, where to go, this, so minus 1/4 sine 2u plus 1/2 u from 0 to n pi. Okay, this notation from 0 to n pi tells you you're going to input the integration limits into this. So it's all of this with n pi minus all of this with 0. So let's go ahead and do that. Yeah, that's okay. A squared. And all of that equals 1. Okay. So I've got 1 equals a squared over n pi quantity minus 1/4 sine 2 times n pi plus 1/2 n pi minus, so this is the minus part, minus 1/4 sine 0, well, plus 1/2 times 0. Okay, well, sine, here we go. So it's minus 1/4 sine 2 n pi plus 1/2 n pi minus quantity minus 1/4 sine of 0. Well, sine of 0 is 0. That makes life easy. So I'm just left with this part. So I've got 1 equals a squared over n pi times minus 1/4 sine 2 n pi plus 1/2 n pi. Okay, for any value of n, 1, 2, 3, 4, whatever, this becomes a value of pi. So some integer value of pi. So this whole thing goes to 0. Lovely. And if that's the case, I'm left with 1 equals a squared over n pi times 1/2 n pi. Oh, how glorious! Wait, what? So a squared, oops. I think I'm missing something. Nope, my n pi's cancel. I've lost an a somewhere. Oh, there it is. I've lost my little a. So this a times a squared, a, little a, little a, little a. There we go. That makes more sense. So now, see, I always lose something if I go rogue off the notes. Okay, so now I've got, let me rewrite this. 1 equals a squared, little a, divided by 2. Solve for a, or solve for big A, I should say. So I've got 2 over a is equal to big A squared, which means a is equal to square root of 2 over a. Wow, that was a lot of work for that a is equal to the square root of 2 over a. But let's put that back into our equation and talk about what that means. So psi of x is equal to 2 over a 1/2 sine n pi x over a. Go team. This is the normalized wave function for the particle in a box. You are going to use this time and time again. You might actually have a 2 over L. Little a is just whatever the length of the box is, the dimension. So what this means is that if you were to, and this is a fun thing to do, if you were to take h psi of x, so the Hamiltonian, which is minus h bar squared over 2m d squared dx squared, if you were to do this, take this operator on this wave function, you would get the energy and the wave function back again. And I encourage you to try it, where you get the energy equals h squared n squared over 8ma squared. There's that little a again, and there's that n. So this n is what we call the principal quantum number. You may have heard of it. Well, it's a precursor to the principal quantum number, where when we do this for the hydrogen atom, you might remember that quantum number n is related to the energy level or the period on the periodic table. That's what this is. Well, it's a precursor to it, because we need to impose the basically hydrogen atom boundary conditions. But this n quantum number is called the principal quantum number. And it's going to give us a lot of insight into how we describe electrons bound to nuclei. Okay, so if you were to do this, and I encourage you to do so, and you might actually have to do one in your homework. So if you were to take the Hamiltonian of this psi of x, you'd actually get h squared n squared over 8ma squared. That's cool. So you could check yourself. So what does this mean? Well, let's go ahead and plot psi and psi squared. Okay, so here's psi, and psi squared is equal to 2 over a sine squared n pi x over a. All right, so psi is known as the probability density. Or sorry, psi is just the wave function. So if I were to plot n equals 1, it would look something like this. Okay, so here's psi. And if I were to plot n equals 2, it would look something like this. N equals 3. Now I'm drawing these offset from each other just so you can see them. They'd actually be at the same value, but you're just extending them out. But you can see that for n equals 1, there are 0 nodes, whereas n equals 2, there's 1 node, or a place where the wave function crosses the x-axis or is equal to 0. So psi of x equals 0 here. Likewise, there are 3 nodes. Psi of x equals 0 at the nodes. Okay, it also equals 0 at the boundary. And so if you were to take psi squared, however, which is psi times psi, you would get the probability density. And so you'd get something that looks like this: n equals 1, n equals 2, n equals 3. And this is where quantum gets weird. In the n equals 3, if you were to look down in the box, you'd think that with a classical particle, if you were to look in the box, the particle should exist anywhere. If you had a ball in a box, you should be like, well, it should be kind of anywhere within that box. But for n equals 2, it's going to be 2 probabilities: a likelihood of being right here and a likelihood of being about right here. Whereas in the n equals 3, it's a likelihood of being at any one of those spots where your probability is highest. Isn't that weird? Whereas here, the likelihood is the probabilities in the center, and you have a lower and lower probability as you get closer to the boundary. Cool thing about this is as you increase the n value, as you get to higher and higher energy states, that quantized n, let's take this to the extreme. Let's go n equals huge, like 45, why not? It's going to look something like this. So if I were to extend this out, it's going to look something like this. With 40, if it's 40, n equals 45, there are going to be 44 nodes. So 44 places that it crosses the x-axis. What that does is that actually starts to look like a constant probability. This is what's called the Bohr Correspondence principle. Realizing I'm probably in front of the board most of the time. I am so sorry about that. Okay, so this is known as the Bohr Correspondence principle. And what that says is as n gets big, n goes to large, classical or quantum goes to classical. What does that mean? That means as you have a larger and larger n value, you're going to have closer and closer energy states. So the energy states are going to become so close to each other, they're practically continuous. Continuous energy states is what the free particle was experiencing, which means that you get more and more closer to classical physics, which is Newton's equations, or are Newton's equations. Okay, quantum mechanics is when you have discrete quantized energy levels, energy state 1 and energy state 2, I should do it like this, and nothing can exist in between. Continuous energy levels is you can be anywhere in between. And as n gets really, really big, the energy states gets closer and closer, such that the Bohr correspondence principle takes hold, and your quantum mechanical result reduces to the classical result, which means you have equal probability anywhere within the box. Go team. Awesome. There is a podcast associated with particle in a three-dimensional box, which introduces the idea of degeneracy. So please listen to that. And it's kind of semi-self-explanatory. We won't go through the mathematics of converting this to 3 dimensions, but please listen to that podcast and follow along in Atkins. Email with questions. Go team.